Hi, Physics 2. Mr. Janowski here with the next part of the chapters 15 and 16 slides on special and general relativity. So, do now. First question. When was Einstein's Annus Mirabilis? That was 1905. That was his miracle year. What a wonderful year he had in 1905. So, question 2. If I were driving towards you at 50% the speed of light, so 0.50 c, at what speed would you measure the light from my headlights? You would measure it to be exactly 100% c, the speed of light, because of the second postulate. And also, the second postulate will answer our third question. If I were driving away from you at 99% the speed of light, 0.99 c, at what speed would you measure the light from my taillights? You would also measure it to be exactly c, the speed of light. So when you're doing the relativity stuff and you're dealing with the speed of light, you can't just add it the way Galileo did back in the day, the same way you add velocities with pitches on trucks and things like that. Light is different because of the second postulate, the constancy of the speed of light. So, then there's this video, which we actually watched this video in the class before, but it's about Einstein's miracle year and the 4 wonderful papers he did that year. So, in the previous classes, we talked about time dilation. So, moving clocks will run slowly. This is called time dilation. Something that goes along with that is called length contraction. So, moving meter sticks will get shorter in the direction of their motion. This is called length contraction. So let's start with a meter stick, which we will say is exactly 1.00 meters long, which is why we call it a meter stick. If that meter stick is moving past us in the x direction, we're going to measure it to be less than 1.00 meters long, which is a little bit weird. So note that both meter sticks are equally tall. So yes, our meter stick is getting contracted, but only in the x direction. In the y direction, it stays the same. In the z direction, it stays the same because it's only moving in the x direction. So these things don't shrink equally in all directions. They only shrink or contract in the direction that they're traveling. So if we have several, this is the Star Trek kind of spaceship. So several of these ships are going to fly past us at very high velocities. So the first one here, well, it's not flying past. This one's just at rest. So it looks normal. One that goes by at 20% the speed of light looks a little bit contracted. 40% looks a little bit more contracted. And so forth and so forth. Until if it's going 99% the speed of light, it is very contracted. It looks very, very smushed. So the question is this going to be a problem for the crews? Are the crews getting crushed by this contraction as this is going on? Are they getting flattened, pancaked? And the answer is no, the crews are fine because the crews on these ships are in the frame of reference of their ship. And as far as they're concerned, it's not moving. So they don't feel this contraction at all. Something else is contracted for these guys. So what is contracted? The distance in which they travel. So if they're heading, east, which is a weird thing to say in space, if they're traveling to the right through space, that direction is getting compressed. So when we were doing time dilation, we had proper time and observed time. When you're doing length contraction, you have proper length and observed length. So the person who will measure proper length, L naught, is the one who's at rest relative to the endpoints of the distance being measured. So let me just read it off the slide. That'll probably say it more smoothly this way. Proper length, L naught, is the distance between 2 points as measured by an observer who is at rest with respect to both of them. So if you're at rest relative to the distance that's being measured, you will have proper length. If you are not at rest with respect to those points, or if those points are not at rest with respect to you, is the equally valid way of saying it, you will measure observed length. So in earlier class, we talked about time dilation and Denise and Alice traveling very quickly to Vega. Now we're going to talk about the length contraction. So they're twins. Denise will stay on Earth. Alice is going to fly off to Vega at a very high velocity. So who is going to measure the proper length for Alice's journey? And the answer is Denise does, because Denise is at rest with respect to the 2 endpoints being measured. The journey starts at Earth and the journey ends at Vega. and Denise is at rest with respect to Earth and Vega. So she's going to measure proper length of that distance. Alice, on the other hand, is on board her spaceship. So Alice is at rest relative to the spaceship. She's at rest relative to the front and back of the spaceship. So Alice will measure proper length for the spaceship, whereas Denise will measure proper length from the Earth to Vega. So who is going to measure proper time for Alice's journey? Well, that's going to be Alice, because the person who measures proper time is the one who is present at both events. So the two events here are Alice leaves Earth and Alice arrives at Vega. So both Alice and Denise were present at the first event when Alice left the Earth, but Denise is not present when Alice arrives at Vega, whereas Alice is. So Alice measures proper time for this journey. Denise measures proper length for this journey. These things get confusing, figuring out who's at rest with respect to this or that, or who's present at both parts. It gets confusing. You just got to think through it. So, yeah, now we do the problem with the math. So, yeah, both twins are 17 years old. Alice flies off to Vega, and Vega is about 25 light years away, so fairly close as far as stars go. She leaves her twin sister Denise behind. So, if Alice goes at 99% the speed of light, how far will Alice claim to travel? So, what is the unknown that we're solving for? The unknown is L, observed length. So we know the proper length. Denise measures proper length. She says, okay, from the Earth to Vega is 25 light years, and Denise is at rest relative to those things. So Denise measures proper length, L naught. Alice will measure observed length, L. That's what we're trying to figure out. How far does Alice claim to travel? So in this case, we know what V is. V is 0.990c. So we're going to do the math part. Take it off to the side. Hopefully you're getting good at this algebra. It becomes not difficult, but tedious. You've got to do all the little steps, do them carefully, write down the numbers. If you try to do 2 or 3 things at once when you're doing this, you'll miss something, you'll skip something. So just please, for now, at least do it very carefully and very deliberately. So yeah, we've taken the ugliness term and we turned it into a number. So back to this, how far does Alice claim to travel? Well, let's start with our length contraction formula. We just figured out the ugliness term. So we're going to plug it in. We know L naught, proper length, is 25.0 light years being a unit of distance. And we multiply that by the ugliness term, and we get this. So the observed length, the length that Alice observes, is 3.53 light years. So Alice and Denise will disagree about how far Alice went. So a couple classes ago, we talked about how they disagree about how long this trip takes. And it seemed like this trip that you want to say is 25 light years long. Well, Alice made that trip, according to her, in only, I think it was 3.56 years. So how can you go 25 light years at 3.56 in 3.56 years if you can't even go the speed of light? The reason Alice was able to do that, and she did truly do that, according to her, is because, according to her, Vega wasn't 25 light years away. When she's moving at 99% the speed of light towards Vega, Vega is only 3.53 light years away. So yeah, time and space are bending, and it's getting weird. So another example with the length contraction. So imagine we're in room 321, and you guys are all sitting there at rest relative to the room, and I'm going to fly across the room in a spaceship holding a meter stick. And I'm pointing the meter stick in the direction in which I'm traveling. So according to you, the meter stick only appears to be 0.6 meters long. So how fast am I going as I travel from one side of the room to the other? So again, proper length can be very confusing. So how it works is I'm holding the meter stick. So I am at rest relative to both ends of the meter stick. Therefore, I measure proper length, L naught, of the meter stick. You guys, meanwhile, you're at rest relative, well, before I even say that, because you guys are not at rest relative to the ends of the meter stick, you will measure observed length of the meter stick. Now, if we're talking about the room, you guys are at rest relative to both sides of the room, so you measure proper length of the room. Whereas I am not at rest relative to those things, so I measure observed length of the room. So I get proper length of the meter stick, you get observed length of the meter stick. You guys get proper length of the room, I get observed length of the room. And so in this situation too, who is going to measure proper time of my journey? Well, remember, who measures proper time? What do you need what needs to be true for someone to have proper time? They need to be present at both events. So the two events are my journey begins at one side of the room and my journey ends at the other side of the room. And the person who is present at both of those events is me. So I measure proper time in that situation. So we're going to try to figure out how fast I'm going. So the thing we're looking for is V. So in this situation, we know observed length L, we know proper length L naught. Plug them in, and then find your own way to do the math. I mean, you can do it my way. I'm showing you, a way I thought is going to be easy to learn. But yeah, if you have your own style for doing the algebra, as long as you're showing me enough work and I can see what you're thinking is, I'm happy. But anyhow, when I'm doing these problems, what I would recommend is sometimes you do actually plug in the numbers earlier. So all of last year, I said, uh, stick with the letters, keep the problem in letters for as long as you can, and just put in all of your numbers all at once at the end. And that would still work for this kind of problem. But honestly, in some of these relativity problems, it's way easier if you plug in your numbers a little bit earlier. Saves you a lot of writing. So that's what I did here. I knew L and L naught, so I turned it into this. Okay, well, I divided 0.6 meters by 1 meter. So the units cancel out. Now we just have a dimensionless number, 0.6. And then ultimately to get to the V, I need to square everything, yada, yada, yada. You do the math, you do the stuff, you get the thing. So it turns out I'm traveling across the room at 80% the speed of light. And again, let me point this out. When you're doing the relativity problems and you're asked for a velocity, you typically want to give the velocity has some fraction of the speed of light. So 0.800 c, that's perfectly acceptable. You don't even need to switch it to 80% the speed of light. I just did that because it's a little easier to understand the idea there. But one thing you really don't have to do unless specified is actually turn it into a velocity in meters per second. You rarely need to do that when you're doing these problems. So quick review. Who measures proper time, delta T naught? Not in the problems we were discussing, but just in general. The person who measures proper time is the one who is present at both locations. So proper time, delta T naught, is the amount of time separating two events that occur at the same location. So in order to measure proper time, you need to be there at both locations. And there's your time dilation formula. And who measures proper length? Proper length, L naught, is the distance between 2 points as measured by an observer who is at rest with respect to both of them. So you need to be at rest relative to the distance being measured, the start and end point of that distance, in order to measure proper length, L naught. And there is your length contraction formula. And you see that they are kind of similar looking, easy to flip up. So yeah, make sure you're grabbing the right formula. And yeah, hopefully you guys found this helpful.